have you ever written just one line of code and then stopped and thought, wait, how does this actually work? How does something like int a equals 10 plus 20 go from my screen to the computer's actual brain? Well, today we're going to follow that single line of code on its incredible journey from a human idea all the way to a machine action. You see, at the heart of all programming, there's this fundamental disconnect. And a great way to think about it is this. We, the programmers, we're like poets. We think in these beautiful, abstract concepts and logic. But the computer is just a worker. It doesn't understand poetry. It doesn't get the big picture. It only understands simple, direct instructions, like a series of taps. So this simple line of code, this is going to be the hero of our story today. To you and me, it's just basic math, right? But to a computer, it's a completely foreign language. So how in the world does this instruction get translated into a series of simple taps that the machine can actually follow? That is the core question we are going to answer. To really get how this translation happens, we first have to appreciate just how incredibly different these two worlds are. The world of us, the human poet, and the world of the machine. Okay, so here's the absolute crucial point. We write code that looks a lot like English and math, but the computer, it's just a physical device. It doesn't see numbers or letters or anything like that. It literally only sees the presence or absence of electricity, a high voltage, which it calls a 1, and a low voltage, which it calls a 0. And that's it. Seriously, that's the entire language of the machine. So to bridge this massive gap, we had to invent translators. In the very beginning, we actually tried to speak the machine's language with pure ones and zeros. It was brutal. Then, we created a middle ground called assembly, which used short little English codes. And finally, we developed high-level languages, like C, which let us write in a way that's much more natural for us humans. All right, so now we know why we need a translator. The next thing we need to understand is the place where our instructions are actually going to be carried out. And I want you to think of a computer not as some magic box, but as a highly organized professional kitchen. And this whole kitchen layout isn't just some random metaphor. It actually has a formal name, the von Neumann architecture. This is the fundamental blueprint for pretty much every computer ever made, and it breaks the machine down into a few key logical parts. So let's see how this kitchen analogy maps to the real computer parts. The CPU? That's your chef, the one who does all the actual work. The RAM, or memory, that's the kitchen counter, holding all the ingredients the chef needs right now. The hard disk is like the big cold storage room for everything else. And this is a critical one, registers. Think of those as the chef's personal chopping board, an ultra-fast little space right in front of him where the real action happens. Now, this is maybe the most important rule of the kitchen, so listen up. The chef, our CPU, he cannot go to the cold storage, the hard disk, to get ingredients. It's just not allowed. The program and all the data it needs must first be brought out and placed on the kitchen counter, the RAM, before any work can begin. Okay, so we have our recipe, our code, and we know the kitchen layout, but our chef only understands binary, those ones and zeros. So how do we translate the recipe? Well, we send it through what you can think of as a code publishing factory, and this whole process has a name, compilation.
Now, this isn't just one simple step. Oh no, it's a whole 4-stage assembly line. First, an editor called the preprocessor cleans up your code. It removes your personal comments and adds in standard content. Second, a translator converts your C code into that middle ground assembly language. Third, a typesetter turns that assembly code into pure binary, the machine's native tongue. And finally, a binder stitches your code together with all the other library code it needs to become a final, finished program.
And get this, let's look closer at that very first stage. You see that innocent little #include line you always put at the top of your C file? It's not just a suggestion. The preprocessor literally takes the entire contents of that file, we're talking sometimes thousands of lines of code, and pastes it right into your program. So your tiny little file suddenly becomes huge before it even gets translated. So, at the end of this whole factory process, our poetic, human-readable code has been totally transformed. It is now nothing but a sequence of ones and zeros, those simple taps that our worker, the computer, can finally understand. So the factory turns our code into binary. But for that factory to even understand our original code, that int a equals 10 plus 20, the C language itself needs to have a set of rules. Specifically, rules for how to handle our data, like the numbers 10 and 20. In C, This idea is called data types, but a much simpler way to think about it is as container theory. And it's really just common sense, right? You always choose a container based on what you need to store. You wouldn't use a giant bucket to hold a single coin. C is all about efficiency, so it gives you different size containers for different kinds of data. So for our numbers, 10 and 20, we use the int data type. As you can see, it's kind of like choosing a small Tiffin box. It's perfect for a standard whole number. Now, if we were dealing with massive decimal numbers, we'd need that giant water tanker on the right, which is like the double data type. So when we write int a, we're basically telling the computer, hey, set aside a small Tiffin box-sized piece of memory for me and just label it a. And what about the plus and equal signs? Well, those are our tools. The language calls them operators. The plus sign is the tool for adding things together, and the equal sign is the tool for taking the result and putting it into our memory container A. Simple as that. All right, we've seen the two different worlds of the poet and the machine. We've toured the kitchen's layout, we've walked through the translation factory, and we've learned the rules for containers and tools. Now, let's put it all together and trace the full journey of our single line of code. Here it is, the complete story, start to finish. 1. You type the code on your keyboard. 2. The factory compiles it all down into pure binary. 3. The operating system loads that finished program into RAM, our kitchen counter. 4. The chef, the CPU, fetches the instruction and uses its personal chopping board, the registers, to do the addition. And 5. The final result is stored right back in RAM, inside that little container we labeled A. And after all of that, the analogies, the architecture, the entire factory pipeline, the chef, the kitchen, what do we get? The number 30. All that work, all that incredible complexity, just to calculate a simple number. So what are the big ideas you should take away from all this? First, just remember that we and computers speak totally different languages, and code is the bridge. Second, that bridge is built by a factory of tools called a compiler. Third, the computer itself is basically structured like a kitchen, with a chef, a counter, and cold storage. And finally, the programming language itself has specific rules for containers and tools to get the job done right.
But you know, the truly amazing part is that this entire journey we just explored, from poet to worker, happens in a fraction of a second. It happens millions of times over, every single time you click an icon or send a message. It really makes you wonder, what other invisible factories are running just beneath the surface of our digital world?